拡散 MRI 技術の基礎から臨床応用までを確立した先駆者として、急性脳梗塞治療などへの活用により MRI の世界的普及への貢献で2012年本田賞を受賞。フランスのニューロスピン超高磁場 MRI 研究センター所長を務める傍ら、京都大学にも研究室を構え、頻繁に日本とフランスを行き来して拡散 MRI 技術の応用・発展に心血を注いでいます。その技術は体の中の水へ問いかけるコミュニケーションとも言えます。博士の目に映った水の神秘、そして人々の生活に欠くことのできない重要性、そこに未来の扉を開く鍵があると言えましょう。それではルビアン博士、お願いいたします。Ladies and gentlemen, please welcome Dr. Bihan.
Good afternoon. It's a great honor to be with you today, and I'm very, very thankful to the Honda Foundation for inviting me again to share with you some of my views about how I can see the future regarding eco-technology. And as you may know, we are doing a lot of thinking about a tiny molecule, which is carbon CO2. And because of the productions of a global warming, effect on climate, effects on environment, and so on. And of course, these changes in the climate have also very, very large consequences on, for instance, on the water. And that's what I'd like to show you today. For instance, typhoons. And my talk will focus mostly on this other tiny molecule, which is H2O, so just water. The blue gold, as we know it, which is, of course, very beautiful. And I'd like to remind all of us that water is really a key actor for life on Earth, as we know it. And I'll show you that it may be even more than what you think. Water has always been associated with life. Without water, we cannot have any life as we know it today, at least. And most of the cities in the world have been built next to water, like river or sea, and of course, Japan is no exception. Unfortunately, water may also be associated with death. For instance, because we lack of water. And this is, of course, terrible, but that may happen in the future if we don't pay attention. Too much water is not good either. For instance, tsunamis and floodings. And water, we have to consider also it is a very small molecule, has a lot of power, mechanical destruction, if you like. So I think that of course, CO2 is very important, but H2O might play a bigger role than CO2 in this current century. People may fight to have access to water. But maybe not all waters are equal, and I'm lucky to live sometimes in Kyoto. Kyoto water is very important, but not only in Buddhism, water has a sacral value. I think there is no chance. Most religions have incorporated water in the thinking, probably because humankind has to have a very strong attention to water. And of course, the Kyoto water is so good that we can make beautiful kimonos, we can make good sake. So I guess now you are convinced that water is very important. So water is a very strange molecule. Very interesting properties that are not completely explained today. Of course, you know very well that the temperature for water to become boiling is 100 degrees, and for freezing it's 0 degrees. But I'd like to point out something very special. Ice is floating. It should not be like that. For other molecules, when it becomes solid, it drops at the bottom of the liquid. And unfortunately, this is responsible, for instance, for tragedies such as the Titanic, big tragedy. Also, it explains why on your whiskey, you have the ice floating. Why? Why is that? It's not clear. Another very important property is that water is very helpful to control temperature. This is why we are sweating a lot during the summertime. This is also why babies are so sensitive to heat, because they have a large surface and they have evaporation, which could be dangerous for them if it's too much. Water also is very important if we consider all the molecules we have in the body, proteins, macromolecules. The shape of those molecules comes from the interaction with water. So we know those facts. We know water is H2O, 2 parts hydrogen, 1 part oxygen. But David Lawrence said that there is a third thing that makes it water, but still we don't know what it is. So I have to say that the water molecule itself remains a mystery. So let's see in more details what the water molecule is about. So again, oxygen atom to hydrogen atom. I call it the single water molecule. But this is dynamic. Everything is moving all the time. So let's take a sushi, for instance. If you press with chopsticks on the sushi, water will come out. But the fish is dead, of course, even if it is very fresh sushi. How is that possible? Well, in fact, we have to remember that there is what we call the hydrogen bond. Water molecules get sticky, not only between them, but also to the proteins which are present in the fish. So all those molecules of water are always bound to other macromolecules. And this is very crucial to explain life as we know it. Without those hydrogen bonds, without the special angle, 104 degrees, between the two hydrogen and the oxygen, there will be no life on Earth. But water is social. A single water molecule doesn't exist. Water molecules have to be related. They have to communicate. They are organized like that. And if you take now the statistics about those networks, water may not be H2O anymore, and some physicists think we may describe water as H3O2 because they are sharing hydrogen atoms between them. So if you look at the Facebook network and the water network, you can see some analogies. So we have to consider that water in tissues is organized as a network. And we should never forget that we are water. 60 to 70% of our body is made of water. 75% of our brain, maybe 80% of our brain is just water. So we think with water. And that's what I'd like to show you soon. So let's go to my own research, which is using magnetic resonance imaging to investigate the human body and the brain especially. So magnetic resonance imaging, or MRI, uses a very strong magnet, and with this magnet, we will magnetize water, or more precisely, the hydrogen nuclei of the water molecule. But let's say water. This is, for instance, a slice of the brain, a vertical slice of one of my colleagues, so very well alive, very healthy. You can see beautiful contrast between gray and white matter. You can see some details such as vessels. All of this comes from the magnetization of the water molecules, which is different between gray and white matter. Why? We have no idea, but it's beautiful. With the technology of MRI, we can see the vessels coming out of the heart, going to the brain, for instance. We can see what's going on after we have a meal, for instance, digestions, and so on. And, of course, we can see beautiful images of the brain. So this is not a brain. This is an artificial brain. It is a virtual brain. Sometimes I call it an avatar of the brain. But this will give us many, many details about how the brain is made. Let me give me some examples. Our brains are very similar because there is only one humankind. So all the brains are about the same. But if you look at details, look at this red line here, which is the limit between areas linked to the motor system and areas in the back linked to how we sense, for instance, when we touch our fingers. So everybody has such a structure in the brain. But the location, the exact location, the exact shape is highly variable. So what I want to say is that we make what we want of our brain. If we look at the hippocampus, a very small area we have in the brain, well, not so small, in fact, it is linked to memory. In fact, the Nobel Prize in Medicine this year was given for people who have discovered that. And we look at London taxi drivers, who are very good. Japanese drivers are very good also, but the study was done with English taxi drivers. They have shown that the hippocampus is bigger in size in taxi drivers than in normal, not taxi driver people. Just because taxi drivers use their memory to navigate, they have increased the size of the hippocampus. Pianists also. Pianists and other musicians have also overdeveloped regions of the brain, which are, for instance, used to have a coordination between the hands. And this plasticity is occurring very fast. In this example here, young people, students, have been taught to learn how to jungle every day for 10 minutes. After just a few weeks, we can see that some parts of the brain are developing because they have to do something about the efforts about spatial localization. So this is going on all the time. So I'm sorry to say, at the end of my talk, I will have modified your brain a little bit, and you will have modified my own brain, because there is already some interaction going on. So this is about the shape and the anatomy of the brain. Now we can do even more, and that's what I call the image resolution. We would like to see what's going on in our brain when we think. In fact, we know very well that there is a link between function and localization. Each part of our brain is dedicated somewhat to a function. So if we can image the brain and see which part of the brain is activated, we have some clues about what the brain is doing. So with MRI, it's possible to do that now, to look deep into your brain without any invasive way, without any surgery. Just normal people can go to a magnet and we can discover many things. This is called functional MRI. When you look at this screen, the image comes from your eyes to the back of the brain. And then it is shipped to the front part of the brain so that you can recognize what you have on the screen. And Professor Seiji Ogawa, a good friend of mine, developed a method to do that. So let me explain briefly what it is about. We know, in fact, this was known back in the 1880s, so long ago, that in the regions of the brain which are active, there is an increase in blood coming up. There is more blood in activated regions. Now the blood is red because there are red blood cells inside the blood. And the red blood cells are red because inside there is a very important molecule called hemoglobin. Hemoglobin carries oxygen from the lungs to the tissues, especially, and not only the brain. But the hemoglobin molecule contains an atom of iron. And as you may guess, in the strong magnetic field of the magnet, this iron atom can be magnetized, not only water, but also iron. So, in brief, we have to consider that in the small vessels we have in the brain, if they have to be seen as containing tiny magnets. The red blood cells could be seen as tiny magnets circulating in the small capillary vessels. So the water molecules which are there will sense the presence of flowing blood. So in regions which get activated, there is an increase in the blood flow, and this will translate into a tiny change in the magnetization of the water molecules, which we can detect with MRI and sophisticated algorithm. So let's do a simple experiment. If you close your eyes and you think about a cat, you see a cat in your brain somewhere. But my question is, where is the cat? There's no real cat. And my question was, the regions of the brain which are used to see the real world, are they used also to see virtual images? So I did the experiment. Here you say to somebody the magnet of the MRI system, cat. You can say it in Japanese, it works also. And you have to think about a cat, and 40 seconds later, question, are the ears of the cat pointed? And you have to think again. And what we see is an image of the brain, this way, and the back here is a visual cortex, the region we use when we see the real world. So what we see on our images is that when we just think about a cat, there is a change in the magnetization of the water molecules. Thinking has an effect on the magnetization of water. I mean, this is huge. And the reason, again, is that there is an increase in blood flow in this area because it has been used by thinking of an image. So what we showed during this very simple experiment is that looking at the real world or looking at the inner world would share some networks. And Professor Sadato in Okazaki, at that time he was in the United States, did an experiment where he asked blind people from birth, people who cannot see, who have never been able to see, to read Braille with their fingers. And he discovered that by reading Braille, those people were activating the visual cortex. So it's fantastic. That means that even if you don't use your brain as it has been designed, you can somewhat use it in a different way. In fact, my own view is that there are some circuits in the visual cortex which are shared by real vision, virtual vision, or reading Braille. Reading Braille is just connecting dots in space to recognize letters. So it's a visual function. And we can say from these experiments that blind people can see with their fingers. But we can do even something more fancy. If you think about an object, for instance, vertical or horizontal, we have to consider that at the back of the brain, we have a direct projection. Of course, it's distorted. But if you see something vertical, you see, for instance, that the regions which are activated have this shape, while if you see a horizontal object, the regions are a little bit different. So now if you ask people to think vertical or horizontal objects, you can read their mind. By looking at the images, for instance here, this person is thinking about a horizontal bar. Here, this person is thinking about a very vertical bar. And nowadays, we can even ask people to think about letters, H, E, L, and so on, and we can decode that this person is saying hello. So this is where we are now. And for instance, you can even measure signal activities in the brain to drive robots. This person here is playing this famous game in Japan, but not only in Japan, about seashore, stone, and paper. You know, the children like to do that. So he's moving the hand or just thinking about moving his hand without moving at all. So the computer will pick up the signal in the motor areas, decode the signal, and send some electrical current to engines, to tiny engines in an artificial hand. And you see at a distance, it could be 1,000 kilometers away, the hand moving, just driven by the thought of this person in the magnet. Even maybe more challenging, this is a story of a young lady, 26 years old, who is in a vegetative state after a car accident. And of course, there is no reaction. When you pinch her, nothing. When you ask her, what's your name? Nothing. And the group of Dr. Owen said that, well, let's put this lady in the MRI machine. And they asked the lady, what's your name? No response. However, the MRI images showed the region of the language, like the Broca area, to light up. So this lady, also in a vegetative state, was understanding the question and was even responding to the question. So then they were very, very intrigued and said, could you think that you are playing the tennis? And of course, the lady, nothing. What they see is a response in the regions of the brain which are activated when a normal person thinks about playing the tennis. Madame, could you think that you are moving in your house, exploring the rooms? No response. However, the MRI images showed that the regions which get activated are the same than a normal person would activate by doing the same. So basically, some communication was possible in this lady who was in the vegetative state. Today, it has been shown that about 20% of people in such a vegetative state are, in fact, able to communicate thanks to this kind of experiment. Today, we can use even EEG, so just pick up signals from the surface of the skull. No need for MRI. So I think it's where imaging is driving us. But our brain is like some software, I will not give any name, but with bugs. Here you see probably that dots which are black. In fact, there is nothing. There is no dark dot on the image. This is an artifact created by your brain. So we are not perfect. This is also very famous. You can see a vase or you can see two faces, right? How do you decide what you want to see? So what I want to show you is that you don't decide. The brain decides before you are aware of it. So the image is shown in the MRI magnet for a very short time, 150 milliseconds. And then you press a button. If you want to say, I saw a vase, you press left. If you want to say, I saw two faces, you press right. So under the brain, there is one area in red here, which is dedicated to the recognition of faces. And we have to consider that the brain activity is changing all the time, but we are not conscious about it. It is fluctuating. So that's what we call intrinsic fluctuations of mental states. So at time 0, you have an image. But look here, 2 seconds before the image is projected, this area could be spontaneously activated or spontaneously unactivated. If it is activated 2 seconds before the image comes, you will feel you see faces. If the region is not activated 2 seconds before you see the image, you will say, I see a face. So you see, you feel that you believe that you decide. You don't decide anything. The brain is deciding for you in advance. So let's switch now to something else, just to show you that water is even more important. This is an experiment that you should not do. Anyway, it doesn't work with sake. If you mix up red wine and water, after some point, it gets mixed. This is called diffusion. The reason for diffusion, in fact, was shown by Albert Einstein with his PhD thesis. So he explained this mixing by the fact that molecules, for instance, water molecules, had a random walk, like a drunk man trying to go home. It's just a random. So he made a very sophisticated model with an equation, which is not as famous maybe for you as the relativity equation. E is mc squared. But to me, it's a very important equation because it's a way to link the microscopic world, you see the red wine being mixed, with the microscopic world, it is linked to molecules which you don't see. So let's go back to MRI. Now there is a patient with a lesion here. And as a doctor, the question is, what is it? Is it a tumor? What is it? I'd like to know. But the resolution of the image is only microscopic, millimeter. You cannot say anything. Your dream is to have some, like a virtual biopsy, to be able to see the cells which are in this lesion. So this is what I developed back in '84 with diffusion MRI. So the idea, using Einstein's theory, was to consider that water molecules, because they diffuse, they will fill obstacles, such as membrane and so on. So I use Einstein's model, Einstein equation, and I made a method which can give us some images of this diffusion of water. So we don't see the water molecules one by one. What we see at a microscopic scale is a message transmitted by the microscopic motion of water molecules. If you take water in a bottle like that, it's free for displacement. So that means the molecules can explore a big area. In tissues such as the brain, because it's compact, there are many fibers and cells, and the displacement of the molecules is reduced. So again, I don't want to disturb you with the physics, but on the image, what I made was possible to have a contrast from gray to white, for instance, black and white, about how much movement the water molecules have. So if in a tumor with many cells, diffusion will be reduced. If there is a cyst with like a collection of water, then diffusion will be higher. So the very first application came in 1990. This patient, in fact, I showed you before, had an acute stroke. That means the clot in an artery of the brain, as we can see here, and all the neurons which are in the territory of this artery are dying. We are losing several millions of neurons per minute, several millions of neurons per minute. So it's terrible. Many patients will die, but unfortunately, even those who are not dying, they will suffer from severe handicap. In fact, acute stroke is the very first cause of long-term disabilities. People will stay paralyzed for life, or they will not be able to speak for life. Once they have a stroke, you have to consider it for life. What has been shown is that at the acute phase, diffusion of water slows down. The water movement is decreasing. Why? It's a little bit difficult to explain, but it has been shown even in patients. For instance, this is a patient developing a stroke. You see the white areas. Even you are not a doctor, you see something abnormal. With conventional, with plain MRI, we don't see anything. Only with diffusion MRI. But the miracle is that now we have drugs called thrombolytic agents, which, if given to the patient, will dissolve the clot, reestablish the blood circulation, and the patients are saved. The paralysis disappears. They can speak again. But this has to be done very quickly within the first 6 hours. Otherwise, it's too late because we are losing several millions of neurons per minute. So this is what diffusion MRI can allow. And in fact, this is why I got the Honda Prize in 2012. Water diffusion also is very important in cancer. For instance, if there are many, many cells in a tissue, as in cancer, water diffusion will decrease. If the tumor is benign, or if the tumor has disappeared, for instance, diffusion will increase again. So breast cancer, especially, is very important because there are many, many women concerned. They have mammography for screening, but sometimes we see something abnormal, and we don't know really what it is. So for instance, this lady had a lesion. Even if you are not a doctor, you see that there is a lesion. So she was injected something to make a contrast. So this is why we see the tumor so well. But it doesn't tell us if it is a malignant lesion or a benign lesion. With diffusion MRI, we can obtain information and with colors telling us what is the probability of each part of the lesion to be malignant. For instance, we can see that in the center of the lesion, there's nothing wrong, but at the periphery, it becomes very malignant. And we can decide where to put a needle for biopsy. So, and we can even, using computer software, isolate the lesion and see inside, like the surgeons will do when they operate the patient. But this can be done without any invasion, just by measuring diffusion. Oops, sorry. So next application is that it has been shown that in white matter, diffusion was anisotropic. So what does that mean? Gray matter contains neurons at the periphery of the brain. Everything else is white matter. That means the wires, which are connecting the different parts of the brain. But it was shown that the diffusion of water is faster along the fibers than perpendicularly to the fibers. So my idea, long ago, 92, 94, with some of my colleagues, like such as Peter Basser at NIH, was to develop a mathematical framework so that by measuring diffusion of water in several directions, we can obtain point by point inside the brain the orientation of the fibers. When the diffusion is higher, in a direction the diffusion is higher, we know that the fibers must be parallel to this direction. So this was done in the 1990s, and the idea, of course, was to obtain some connections between those voxels, those points, and this is now very easy to do, and this is what we call the human brain connectome. We can make beautiful images of the connections in the brain. In the United States, they dedicated $30 million to make an atlas of the connections in the human brain. In Europe, we have a little bit less money. We got only 2 million. And we worked with 12 different partners to make images like that, the first images of the connections in the human brain. We have now more than 100 brains like that. It takes 15 to 20 minutes. Just go in a magnet. You don't even have to think about the cat, just nothing. You can sleep. And we obtain these gorgeous images of the connections in the brain. So a very important message, which is that from research, from a new idea to application in real life, it takes a long time, 10 to 15 years. I invented diffusion MRI in 1984, application to stroke 1994. For DTI, so this method for connections of the brain, 1994 was the invention. It's only now that it's used. It's used, for instance, to see that in babies who are only 2 months or 4 months old, before they can speak, the fibers in the left hemisphere, in the future areas linked to language, are more numerous, if you like. There are more fibers already, so the brain of the baby is ready on the left hemisphere to deal with language. In some schizophrenic patients, we can see that the fibers connecting the frontal areas and the areas involved with sounds, audition, are faulty. The connections are not so good. And you know, schizophrenic patients usually hear voices. That may explain it. So now this technique is so popular that in one of the Paris metro stations, they put as an art, a figure, the connections of the human brain. So I think it's becoming very, very popular. So diffusion MRI has been used for many applications, for stroke, for the orientation, mapping of the fibers in the brain, for cancer detection, and it's used now for to detect activation in the brain. So I don't have time to explain everything. I just like to carry the message that we should not forget water. Water is very important, and Pollack said life scientists have ignored the water as a fish forgets water in the ocean. And water, for instance, like in the sushi, may not be organized the same way next to membranes, next to proteins, or elsewhere. And it's known now from the discovery of Peter Agree and McKinnon, who got a Nobel Prize in 2003, that water molecules can cross cell membranes using specific channels called aquaporins. So they are specific molecules which are dragging the water molecules one by one, breaking the hydrogen bonds. So nature has capitalized on water and is doing trick to the water molecule, for instance, to break the hydrogen bond. So cells can say, well, I want so many water molecules in or so many water molecules out. This is heavily controlled. And some drugs now are designed to use those features, for instance, to treat some patients with epilepsy or migraine. If we consider neurons, they have many dendrites. So dendrites are, if you like the antennas for the neurons, but they have hundreds of them. And on each of those antennas, we have some connections with other neurons. One single neuron can be connected to 10,000 other neurons. Think about your cell phone. Cell phone connect with 10,000 contacts. It's huge. And we have 100 billion neurons. So the connections are huge. And Raymond Icahal, who invented the concept of neurons, said, neurons are the butterflies of the soul, which could reveal someday the secret of our mortal life. I think he was completely right. And he also said that the swelling and contraction of all those structures was probably a key element to understand how the brain works. And this is what diffusion MRI can reveal also, what I call the neuromechanical coupling hypothesis. So the changes in the size of the parts of the neurons linked to the water movement can be detected by diffusion MRI and are pointing out to maybe how the brain works. So this is where we are today. We can obtain images of brain activation, even in people in vegetative state. We can obtain beautiful images of the connections in the brain, but that's not enough. We need to understand more. We have about 20,000 genes, but as I said, 100 billion neurons, each of them connected to up to 10,000 other neurons. So genes cannot explain our brain. We have language areas, all of us, but genes cannot say if I use this area for French, for English, or Japanese. This is the environment. So this is what we want to understand. What I call the neural code, how the organization in space of the neurons along the cortex make it specific for language, for vision, for motricity. This is completely unknown today. So we have to address the right scale. We have to go now to very high resolution images so that we can understand diseases better, to have early detection of diseases. Maybe we can reprogram the brain after some injuries. That would be a dream, but I think it's possible. We'll have to wait. So how to do that? Well, MRI is about magnetization of water molecules using a strong field. So this is just to give you an idea. This is a magnet you have on your fridge, 0.005 Tesla. It's a unit for magnetic field. In hospitals, magnets are usually 1.5 Tesla, so 30,000 times the Earth's field. 30,000 times. Nowadays, including Japan, we can find machines working at 3 Tesla, 60,000 times the Earth's field. And there are a few machines you will get this year. I think you will have 5 in Japan working at 7 Tesla, 140,000 times the Earth's field. And there are a few machines working at 9.4 Tesla. So you see there is a race for high field. Why? For instance, look at the hippocampus. This area of the brain, which is overdeveloped in London taxi driver. In fact, this area, which is linked to memory, is the first to be hit in Alzheimer's disease. So if you have a way to see this area very well with great details in patients at the early stage, we might think that we may help them with diagnosis and then slow down the disease progression. We don't have a treatment, but at least we can delay symptoms. So these are images, for instance, of the hippocampus obtained at 7 Tesla. But our dream is to go even to higher field. The problem is that to see costs a lot of money. So we have to share, and physicists know very well how to share. They have huge instruments. That's the LHC, where the Higgs boson was discovered recently. At the RIKEN also, I know in Japan, there are huge facilities. For nuclear fusion, you know that in France we have the ITER site to produce energy for nuclear fusion. Japan is like one of the leaders for this. So this is how I decided to convince my bosses, if you like, and the administration, politicians, to build in France a place where we can have a very high field MRI system. And the target is 11.7 Tesla, so 220,000 times the Earth's field. So this is a magnet. It's huge, 5 meters in length, 5 meters in diameter. It will be the first in the world of this intensity to scan the brain. It was designed by the physicists of my institution at the Atomic Energy Commission. And it's under completion now. And it will be installed at NeuroSpin. It will be cooled down at minus 271 degrees, so 1.8 Kelvin, in order for this magnet to get the right field strength. So it is today built in a factory called Alstom in France, where they make the French TGV, where they're also making for you in Japan some special magnets for nuclear fusion. So this is how the magnet looks. You know, it's almost finished now. It's incredible. And just to show you the precision, this is a coin. This is a French coin, European coin. And this, in the black, I don't know if you see it, the black line here is the position of each of the 170 pancakes that we have to put in the magnet. The location is extremely precise, and this is crucial. So we are building what sometimes I call a human brain explorer. And we will get this magnet in about 1 year from now. Many people thought it was not possible, so I like this, that they didn't know it was impossible, so they made it. That's our case. So to finish, I'd like to comment on the motto of the Honda Foundation, which I like so much, creating a truly human civilization. Sustainability is crucial. I hope I convince you that water is absolutely necessary. Global warming might change access to water. People may fight. Wars could be started because of access to water. And also water and natural disasters. So water appeared on Earth, and this is how life could be created. So life came thanks to the water, cells, organisms. So life frontier is about this kind of life. We need to have early diagnosis and treatment to have longer lives. But longer lives are good only if we have happy lives. So we have really to understand mind disorders and see how we can cure them. Population will be growing, so access to water will be even more a challenge. So water has permitted life, and life has permitted intelligence to come. And this is what I call the wet human brain. The brain works with water. And science and technology is, of course, using our brain to analyze situations, to propose solutions. I think scientists should be considered as a reference frame for knowledge, but only if they remain neutral and trustable. So this is not always easy. But the next step, which is a little bit scary, is that from water to life to intelligence, we are steering to what I call dry intelligence, dry computers. Maybe dry computers at some point will not need us anymore, so we have to be extremely careful about how we control these technologies and how we interface with water. But maybe this life without water is necessary if you want to explore the universe. So with those words, I'd like to show that the vision of Honda Foundation is really, really timely. In English, maybe it's not so easy to go deep into the roots of this vision. For instance, if we consider that life, the heart, is very important, this is something maybe we cannot find in dry computers. So we have to be sure that we're able to preserve our emotions, our way of living. And this is a direction. This is where we go. This is not something we have achieved. This is what should drive our research. So diversity, biological, nature, that's very clear. But now we have to respect cognitive diversity, how people have different ways of thinking, we should be respecting them. And we should focus on young people because they are our future. We have to show them diversity is important. And we should also invest and protect all people because they have a huge quantity of knowledge that we have to learn from them, and they have to be able to share it with us. So we should do our best to protect the well-being of all people. And I thank you very much for your attention.
Thank you very much, Dr. Lubian. それではここで皆様からの質問をお受けしたいと思います。
非常に興味深い話を聞かせていただいて感謝をいたします。で、質問ですが、水分子が水分子と、離れたりひっついたり離れたりする水素結合の過程はタンパク質などとの相互作用では生体内の水、H 酸素や水素以外の原子や分子とやはりくっついたり離れたりするネットワークを作っているのでしょうか。どんな原子や分子ですね、生体内の水以外の分子や原子がそのような水との揺らぎの相互作用をしているのでしょうか。その点をちょっと伺いたいと思いました。
Yeah, so if I'm not sure I understood everything you wanted to address, but I have to say that, of course, my talk was mainly on water molecule, but water molecules, in fact, are responsible for the shape of many other molecules. And with MRI, for instance, we are now, especially with high field, trying to see ions such as sodium. We are also trying to see metabolites, neurotransmitters. In the brain, it's very important also to see how the different molecules activate neurons. So my vision is that water molecules are responsible for the shape of those molecules. And as you pointed out, there is a lot of dynamics in all these problems. And I think this is something we forget. People usually have a fixed view of the system. For instance, the brain, neurons, connections, but people don't realize that everything is moving all the time, and water molecules have a very crucial role. So maybe it's not exactly the question you wanted to cover, but we have not enough time probably to go to everything. Yeah.
はい。
今のおっしゃるのは分かったんですけど、水のH2O という、水素や酸素の原子、あるいは H2O という分子が他の例えば窒素とかリンとかですね、マグネシウムとかカリウムとか生体の中の、原子や分子の形を作るときに水の、構成要素が他の原子や分子と、離れたりくっついたりする揺らぎの相互作用をしているのでしょうか。直接的な相互作用があるのでしょうかということをお尋ねしているんです。
はい。その分からなかった。そう。多分でもまだ分からない。はいはい。
こうした医療機器の発達や医学の発達というのは人間の長生きをする上では非常に大きな役割を果たしていると思います。一方では先日アメリカ合衆国での女性の尊厳死の問題のように人間の生き方とのバランス、長生きをすることが全てかというとまたそれとは難しい違うところもあるかと思いますが、医療機器や医学の発達というものとそういう尊厳死、それから生命維持というようなこととですね、そのあたりのバランスについては先生はどのようにお考えでしょうか。
So you are talking specifically about breast cancer or other kind of cancers as well? So when
がんに限らず医学全般ということで。
So the problem today is, I think, I'm talking about breast cancer because I think it's a very important issue. Women when they have something abnormal on the mammography, they may have surgery. They may, as you said, they may get very invasive treatment. But sometimes, and there is nothing wrong. So this is very costly psychologically for the women, of course, but also for economy because they have to go to the surgery and they have to get invasive treatment. Sometimes we have to remove the breast. Also, maybe there is no cancer. So with these imaging techniques, we think that we can help surgeons to make the decision. For instance, in our images, if it is red, it's cancer, sure, we have to operate. If it is green, it's not cancer. We may have to monitor for maybe 6 months or 1 year. If it is orange, then we are not completely sure. So this is when you have to put biopsy, I mean a needle to take a sample. The problem is that if you put a needle, there will be a trace later. So when the lady will have a mammogram 1 year later, you have a trace of the needle left. And then sometimes it's difficult to sort out, is it cancer coming or is it a trace of the needle? So we believe that such MRI, with diffusion MRI methods, has the potential to sort out women who have cancers and those who have no cancer. The problem is that MRI is very expensive. So we cannot use MRI as a screening modality. So the idea is to reserve this diffusion MRI to women who are at high risk from genes. For instance, we know that they have a high chance to develop a cancer. So then maybe they could have this technique available. Or ladies who have suspicious lesions on ultrasounds or mammograms.
よろしいでしょうか。ありがとうございました。